Ten wykład jest drugim.
This lecture is the second in a row.
Co było pierwszym?
And what was in the first one?
W ramach pierwszego wykładu.
At the first lecture, I presented the program of the whole course of Mathematical Analysis 1, that is, differential and integral calculus of one variable. I presented the main objectives, that is, a function differentiation, or calculating and determining of a derivative and its application,
Obliczanie, wyznaczanie pochodnej i zastosowania pochodnej.
and the second objective, even the superior one in integral calculus, the definite Riemann article. Well, on traditional lectures, on most of them, I think, such a lecture as this one, in principle, the first substantive one, presents the initial things. The knowledge from high school is recalled, the concepts are sorted, and certain theory developed. Our main goal is the definite integral, and it appears only at the end of the lecture, and sometimes at the next one, and even at the next semester. That is very far. In a while, we are just going to discuss the definite integral. Somehow, we begin from smoke out of a chimney. Some would say, never that way. Well, I think we should place that goal at the first class already, and therefore I do so. My proposal is not to wait until the lecture ends, but to recognize the goal now, to learn what this definite integral actually is, and it could be done, to learn the definition of an integral, its geometrical interpretation, that is also possible. We made the first attempts of calculating a definite integral. We show the first applications, and then there will be a break. We will go create certain theory, and not all, but almost all will be subordinated to that goal. I do it so as we know where we are going. What is our aim? And that what we do is not art for art's sake, but is achieving the objective. We are going to build a theory. If we talk about sequences, about convergence of sequences, limits of sequences, limits of functions, a limit of a function will be a derivative. We will apply derivatives. We will build theories of primary function of indefinite integral and come up to the fundamental theorem, all the time keeping in mind that what is happening is subordinated to what we already know, what we have already touched. Thus, the first lecture is dedicated to the definition of a definite integral. And now we have the following situation. There is a function, x, y, and we have to make a reservation here. We are going to use concepts we do not know yet, but they are intuitive. The concepts will be explained at the right time, and if I use the concept of continuous function, we have the right not to know what it is, but it does not matter. It is important we have some intuition and we master a certain scheme. So the situation is as follows. There is a coordinate system, there is a section AB at a number line, which is actually a set. We are going to talk about it. A set of these x's greater or equal to a, and smaller or equal to b, x's, that is real numbers, and we will talk about real numbers later. Well, we have this limited section. Again, we hear limited section, that is, a limited set. This will also be explained, but intuitively, we feel that it is limited from top and bottom, or each x is limited from top and bottom, that the set is limited. At that set, we have a non-negative function. What is a negative function? This will also be made clear. We have a non-negative function to be drawn like this. This is its graph drawn. It is a function of f of x, sometimes it will be called y, and sometimes y equal f of x in double, different ways. The function is non-negative. This is obvious. Its values are not negative. It all happens within the AB section. Possibly the function is also defined outside the section, but we are interested only in that section. We say the function is definite, or a set of its values is. We are also to discuss it later, but intuitively, we feel that when we project its points to the y-axis, it will be such a set in this example, as I show, such a section, and it will be a set of values, and it will also be limited, only that much, and such functions will be of interest for us for the integral. For the integral, as in the other context, could be indefinite. Well, the function is definite. And why definite? This is not the topic at the moment. However, let's reveal the secret. Indefinite functions will not have integrals in a sense of the definition to be given soon. Well, such is the situation. And now, we want to give a definition of a definite integral of such a function. We perform the following construction. If we take a section AB and treat it as a section in the first partition, the next will come soon. I draw this section AB on the side and select one intermediate point of the section. I do not designate it on purpose. The point could also be at the end. It may be a point A or B, and so it will be in the first step of a certain operation. We say for n equal 1. In the second step of this operation, we take section AB. On purpose, I draw it on the side. We will return to that drawing soon. Or in the second step, for n equal 2, we are numbering the steps. So section AB will be divided to two sections, independent of which point was taken before. We have one section and the second one. Let's select from each section one intermediate point. Let it be this and this. They could be ends or beginnings of individual sections. In particular, take this point, which could be the end of the first section and the beginning of the second one. That is, it could be used twice. The third section, in the third step, for n equal 3, will be the third partition. Now I use the word partition of section AB into three sections. From each one we take one intermediate point. For now I do not designate them, and so on. Let's arrange. We take the indefinite set of AB section partitions. We define inductively. If we have the fifth one, then the sixth one we define independently of the fifth. The nth partition of the section I plot here. It will be partitioned into n sections. Their number is n. The first point, that is, point A, be designated as x0 in the nth partition, point B be designated as x(nth) in the nth partition. This upper index denotes the number of the partition. Further, this point as the end of the first section, if we wish to describe it in this convention, be the first point x1 in the nth partition, next one x2 in the nth partition, the pre-last xn minus 1, nth in the nth partition. Somewhere on the way will be the ith section, ith from the first to the nth. It will be designated as xi minus 1 in the nth partition, and that point xi in the nth partition. Its length is delta xi in the nth partition. In each point of the section, there is n of them in the nth partition. We select one point called the intermediate, and that first point we name KSI1 in the nth partition. It has been adopted that way. I do not want to plot too many points here. In the second one, there is also an intermediate point. In the ith, there is also an intermediate point, and that point is the ith in KSI to the I in the nth partition. And now, with the nth partition and selection of intermediate points, there is n sections, n intermediate points, one for each section. We create the following number, sigma n. And now, before I start to write here, as the expression is rather long, we take the value of the function in the first intermediate point, that is f of x ksi1 in the n. This is the length of the rod here, and we multiply it by the length of the first section. That way, in terms of geometry, we obtain a rectangular area. Plus, We pass this to the second section. The intermediate point is already waiting there. We take the value of the function in the second intermediate point from the second times the length of the second section, and we add a rectangular area again. And so on. We have a definite number of sections. Passed to the ith section. In the ith section, we have the value of the function at the ith intermediate point, and we multiply it by the length of the section and receive a rectangular area. There is n of such rectangulars, so sigma is the sum, now I write it shorter, of function value in the ith intermediate point of the nth partition times length of ith section in the nth partition, where I is from 1 to n. We have created the sigma n number related to the nth partition. What is this number if we would like to interpret it geometrically? It is a sum of fields of the adequate rectangles we have here. And now let's imagine that we have a sequence of partitions. Such sequence of partitions is called in literature the normal sequence of partitions. Well, we define the normal sequence of partitions, that is such a sequence of partitions, that the length of the longest sections in the nth partition, the number of those sections is definite, and the length of the longest one could be fixed, is the sequence converging to zero. I use the concept, a sequence converging to zero, on purpose, even if we do not understand it yet, but we feel those are the numbers that intuitively approach zero. They are smaller and smaller. That is, when we go far enough in the sequence, they will be very close to zero. Well, we operate within normal sequence of partitions. That is, with such a sequence in which the length of the longest section approaches zero, that is, the length of each of the sections approaches zero, which in practice means that such AB section is very densely cut. There remains no part free of partitions. And at last, we come up to the definition of a definite integral. The definition is following. It is rather long in notation, and I will read it, even if it is relatively difficult, complicated, but intuitively simple. And I am going to present it at once. If, for a normal sequence of the AB section partitions and each selection of intermediate points, that is, those KSI I points, the sequence of sigma n numbers corresponding to that sequence of numbers, they are called the integral sums. The sequence of integral sums is always a convergent sequence. Then we say that the function f is integrable. Or, in other words, it has a definite Riemann integral. Function f has a definite Riemann integral if for each sequence of partitions and for each selection of intermediate points, the corresponding sequence of integral sums sigma n, we do not yet understand the concept of a limit, but never mind, we feel it intuitively, as n tends to infinity, it always has a limit. If this sequence converges to the proper limit, to a number, then we say that the function is integrable. Please note how difficult it is to check whether a function is integrable or not, as there are very many partitions, infinitely many. There are intermediate point selections. There are infinitely many of those sigma n sequences. So this becomes extremely difficult and sometimes impossible to check. And yet we have such a definition. And what next? But more on that in a moment. We have given a definition of function integrability. Of what function? The definite one, as it is easy to check. When the function is indefinite, then the limits of such integral sums do not exist, so that we do not need to consider integrability of indefinite functions. Thus, once more, there is a concept of function integrability. When is a function integrable? If for each normal sequence of a section partitions, for each selection of intermediate points, as we have done here, the sequence of integral sums corresponding to those partitions and selections of intermediate points always converges to the proper limits, whatever that means now. Well, notice, we do not have yet the concept of a definite integral, only the concept of integrability. The first remark concerns the existence of those limits of integral sum sequences. Well, it can be proved. I am not going to do this now. that if a function has this property at that section, then for each sequence of partitions and each selection of intermediate points, the corresponding sequence of integral sums is always convergent. Then it can be proven that it is always convergent to the same limit, the same number. We find different definitions of integrability. Some of them say that a function is integrable if sequences of integral sums are always convergent and always to the same limit. There is no need to add. But these are equivalent definitions. When I gave the definition that only limits exist, then while creating such alternative divisions, it could be concluded that the limits will always be the same. But let me remind you that for sequences, when we operate with sequences and subsequences of convergent sequences, then it will come out that a subsequence of a convergent sequence also has the same limit. It will result, and I announce it only. Thus, we have such a situation. We have a function, let's assume it is integrable, that is, for each sequence, a subsequence of partitions and intermediate point selections, the sequence of integral sums sigma n is always convergent and always to the same limit, and that the one and only for a sequence of integral sums, whatever the sequence is, for whatever sequence of partitions and intermediate points selections, we just call, and this is the second part of the definition, the definite integral. And we write it so, integral of f from x by dx, and read, definite integral within the range from a to b, or within the limits from a to b of f function of x. And such a mysterious d of x we have here. We do not yet know why, but it will be explained. What is a definite integral? It is a number, the one and only limit of the integral sum sequence, whatever the sequences are, for whatever the partition sequences and selections of intermediate points, with the assumption that the function is integrable. A definite integral is a number. What number? Well, we present geometrical interpretation of a definite integral. We say a definite Riemann integral. Thus, this is the limit of integral sums. We still do not know the concept of sequence limit, but we feel intuitively that this is such a limit number, such a number, that if here is just such an integral, that around it, in each such surrounding, the expressions of the sigma n sequence already exist from a certain place. That is, the whole sequence is focusing around it, and focuses only around that particular number. We will talk about it when discussing sequences and sequence limits. We interpret the integral. Integral is a limit of a sequence of integral sums, and integral sum, that is easy to interpret, we already talked about it, was a sum of rectangle areas. So, when n tends to infinity and partitions are more dense, as the length of the longest section of the partition in the normal sequence tends to 0, then the rectangles become ever thinner. Lengths of bases are becoming even smaller, and that way we have n, and that n tends to infinity. That is, we have thousands and millions of those sections and millions of those poles, that is, rectangles. And every time the expression of a sequence that we observe, and which tends to the integral, is interpreted as a sum of areas of those small rectangles. So let's imagine that n are already very high, and the rectangles here are very numerous. Then what is the limit number? It is obvious that the limit number is, that is, the definite integral is, we have the right to interpret it as an area of curved line trapezoid limited with the non-negative function graph. Such a function we discussed. X-axis, AB section, a straight line x equal a, and a line x equal b. What is the definite integral? It is the limit of the integral sum sequence, a limit of the sum of those rectangle areas, and the limit sum of rectangle areas in the area of the curved line trapezoid that I encircle with my finger. What is the definite integral geometrically? It is the area of the curved line trapezoid. A few more comments about it. We have given the definition of function integrability, integrability in the Riemann sense, that is, the definite integral of a function. The definite integral is a number. Geometrically, for a non-negative function, I repeat the drawing, but somewhat smaller. We have function f. It was an area of such curved line trapezoid. One more comment concerning designations. This is the number. This is the area of a curved line trapezoid for a non-negative function. Whether someone puts it this way, that it is an integral from a to b of f of t dt, is this permissible? Of course, the letter has no meaning here. Sometimes it happens. We are going to change the letter of the integrated function with respect to some variable. All that happens. Further, some may ask, are we going to calculate using the definite integral only the areas of such curved line trapezoids as at the drawing? Of course not. We're going to calculate integrals from negative functions. If it was a negative function, only negative at the section AB, for example like this, then the definite integral, if existing at all, will be the minus that area. And that results directly from the definition. Well, one could ask, what will happen when a function is non-negative and positive? Let's not go into the details now. So, we are going to calculate integrals from negative functions, but will it be only areas calculated? No. We are going to calculate definite integrals of various functions, limited functions, as I already said, that unlimited functions, as it results directly from the definition, do not have definite integrals. That is, they are not integrable. So we are going to use definite integrals for different things. Soon we will get familiar with the first applications. And even if we calculate some objects, for example, the volume of a solid, then we probably calculate the integral of a non-negative function. But it will be a volume, though the integral of that function may be interpreted as this area of the curved line trapezoid, because this is the general interpretation, but its value will express a completely different quantity than area, and we have to consider it also. Now, it seems to be time for asking questions. Is this definition very difficult? Possibly. Is it easy to check if a given function is integrable? Very difficult. Some would say this is completely useless and will be close to the truth, because interpretation is one thing. That it is an area of such a curved line trapezoid, well, but how to check that the function is integrable at all? And what functions are integrable? If we are to operate any normal sequence of partitions with selection of intermediate points, then these are countless. And each partition needs a description. The intermediate points should be described, some sequences to be created, and then check if they have limits. If every one of them has a limit, sometimes it is impossible to do, whether it is impossible in general, and yet we use such a definition because it is good for the other reasons. Let us not care about this now, that the definition is difficult. Maybe we should anticipate that all functions, whatever that means, continuous at sections A, B, will be integrable. And we are just going to discuss such continuous functions. Remember that important theorem, the very difficult theorem, not the instant one. It requires passing through the bottom integral, the upper one. And I speak to mathematicians now, who probably must know how to prove a theorem that each function continuous at a closed section has the definite Riemann integral. That means they will go through the upper integral, the lower one, the Darboux, pass through different criteria and prove to themselves that the function is continuous, is integrable. And the continuous functions, let's announce it now, is most of the elementary functions, those basic ones, we are going to apply, and we'll discuss here at this lecture and the subsequent lectures. That is, the linear square function, polynomials, quotients of polynomials, that is, rational functions, trigonomic functions, logarithm, exponential function, assemblies. These are all continuous functions, so that the set of integrable functions will be very, very large, but the continuous lines will also be integrable. So what, in the end, I think, we can present ourselves an example and check for a specific function if it is integrable, and eventually how much is its integral. There will be no surprise if I take the simplest function, for which we are able to check, at the stage of definition, that it is integrable. Because if we know that it is integrable, the situation with calculating the integral is different, but we discuss it at the next lecture. Let's take an example of the simplest possible function. Here is a section 0, 1. X-axis, y-axis, and a constant function equal 2. I changed the scale of the axis a little, but never mind. We have a constant function equal 2, that is f of x is 2, x belongs to section 0, 1. Such is the model. This positive function is now a constant function, of course, a limited one. We ask if the function is integrable. In order to check that it is integrable, we have to take any normal sequence of partition for that section. Let's say we have optional partition, normal one, nth partition is here. Now the nth partition has in it n optional sections, no matter what they are now. We select intermediate points, one for each section. What are they? Arbitrary, just any. We write down the integral sum related to that arbitrary fixed sequence of partitions and the arbitrary fixed selection of intermediate points. Now we are at the first section. At this first section, there was the value of function in the intermediate point for the first section. How much is it? 2 times the length of the first section. That is, 2 times the length of the first section. So we marked it in the nth partition, plus. We pass to the second section. The function value in the intermediate point of the second section, again 2, times the length of the second section, and so on, till the very end. It will be 2 times the length of the last nth in the nth partition. It is equal, and we have, I repeat, an arbitrary fixed sequence of normal partitions. We have a selection of arbitrary intermediate points, already fixed, and we create for those selections a sequence of integral sums, which equals 2 before the parentheses, and within the parentheses we have delta x1 plus delta x2, this upper index is still n, but I do not read it, plus delta xn, length of the first section plus length of the second section, and so on till the nth one. Then the sum of those deltas equals to the length of the whole section 0, 1, here just times 1 equals 2. What is the effect? We have taken an arbitrary normal sequence of partitions of just the section 0, 1, an arbitrary selection of the fixed intermediate points, and it comes out that the sequence of integral sums, that any sequence of the integral sums is a constant sequence equal to 2. The question is the constant sequence equal to always convergent? Of course, yes. To what is it convergent? By intuition, to the number 2. This is the limit. Conclusion. Our constant function equal to at the section 0, 1 is integrable, or otherwise has a definite Riemann integral. What's more, that number 2, which is the limit number for each sequence of integral sums, is the integral from 0 to 1 from function 2, dx, and so we could put it all down. Thus, each such constant function will be integrable. That was easy. And if someone wanted to have a non-integrable function, then let him have one. I give only one indication. For example, at the section 0, 1, let him take such a function, to be discussed in the proper time. Let him take the Dirichlet function. For each rational number, let him assign 1, and for each irrational number, the numbers are to be discussed and completed in subsequent lectures, let him assign 0. Once again, for rational, 1, for irrational, 0. And it turns out that such sequences of integral sums could be created, that the sequence of integral sums once will be equal 1, and once only a constant sequence equals 0. There will be different sequences and different limits, and that is not possible in the case of an integrable function. That is, the function is the 2 value, just 0, 1. The Dirichlet function is not integrable. Thus, where are we now? Let's sum up. We have a definition of a definite integral. This is a number, a limit of a sequence of integral sums. we still have it written down. And geometrically, for a non-negative function, this is the area of some curved line trapezoid. And now the target for subsequent lectures. But first of all, the soft target, that we could try to calculate integrals not only for continuous functions, and possibly out of the definition, and it appears that this measure is not the best for calculating. Though it seems to be an intuitive one for calculating integrals, it is intuitive and worth knowing to learn the first application, and then we will develop the theory, we will learn the taste of the theory, and come up to such theorems that integration of such simple functions we will make in our memory.
Realizować w pamięci.